Today I want to start with the free particle, and then I want to introduce the notion of time evolution for a quantum state. Okay? So what is a free particle? Okay, so we have already come across the Hamiltonian operator, which is just a quantum mechanical analog of the classical Hamiltonian function. And what we do is that if you have a classical system and you're able to write down the Hamiltonian functions, which will have for non-relativistic systems, this would be the kinetic part. And if the potential only depends on the position, it'll be some function of V. Then we go to, so this is classical. And then we go to quantum mechanics by replacing momentum by the momentum operator and position by the position operator. And that's how we get from the classical Hamiltonian to the Hamiltonian operator. And once we have the Hamiltonian operator, we go ahead and solve the Schrodinger equation, the time-dependent Schrodinger equation, right? And of course, in the position representation, we haven't really seen any other representation, but just believe me that there exists an even more abstract version of quantum mechanics. In the position representation, P is given by h bar divided by I, d by dx in one dimension, and x hat is given by just x. And then the Hamiltonian operator just becomes minus h squared by 2m del squared by del x squared plus the function of v. Okay? So in this position representation, the Schrodinger equation, it takes the form that we know, and it's good to write this again and again so that you remember all the nitty-gritties. It's one of the most fundamental equations that govern our world, so it's not a bad equation to memorize. Okay. So this is the Schrodinger equation. So let's solve the Schrodinger equation for the free particle. So for the free particle, that means that the particle doesn't have any potential energy. So V of x, this is 0. You can take it constant as well, doesn't matter. But we know that we have the freedom to adjust the 0 point of the potential, and it's conventional to choose that to be 0. Okay. So if you do this, then the Schrodinger equation is as this thing. And implicitly or in some form, we have actually solved this equation already, right? And we know what the solution is. The most basic solution is the solution which has this form. It is a non-normalizable solution, but it has an interpretation in terms of relative probability is given by px minus et. But E is not some random function of energy. E is given by p squared by 2n, right? So this is the free particle, okay? And this is just a particle which is completely delocalized. It has there is no position information about this particle. We know precisely what the momentum is. So if I look at the momentum is P, right? So we can think of, the wave function in the momentum space. So this is the momentum space P. And then we can think of the wave function in momentum space being a Dirac delta function. Then, so this is basically going to be AP, right? It's a Dirac delta function. And then if we do a Fourier transform, then we go to position space, and in position space, it's completely delocalized, right? It's basically constant, right? So this is in position space. Okay, so, and then you know that if you can have a free particle which is somewhat localized, and what you have to do is that you have to take a linear combination of these guys and integrate, if you integrate it over some, some suitable AP, then, this will give you a localized wave function, okay? Is this clear, what we're doing here? So the thing about this, solution is that it's an eigenstate of the momentum operator, right? It's an eigenstate of both H and P, okay? However, this guy is not an eigenstate of P, and therefore it is also not an eigenstate of H. And why is that? Because as we can see, we are integrating over different P's, okay? And see that because there is no potential energy, P and H, they commute, okay? Now, although we won't cover that in detail in this course, but if we have two operators, A and B, which do not commute, say they're Hermitian operators, then the delta A, the uncertainty in observing A, and delta B, the uncertainty in observing B, can be arbitrarily 0. So this means that you can observe both of them with arbitrary accuracy. Okay. Okay, so let's come back to the free particle, which is the eigenstate. And there are two types of solutions here. So let me just define, say, P to be a positive quantity. So this P is, as we said before, P is related to E. P squared is by 2m is my E, right? So that means P has plus minus 2me square root, right? So this is the value of P. That means that, that solution that I wrote down, there are actually two solutions there. One is 1 over square root of, one is e to the power I by h plus P. So 2me times x minus e of t. And there is another solution, which is square root of 1 over square root of 2 pi h bar e to the power I by h bar. There's a minus sign, but let me just factor out the minus sign here. So this has 2me of x, and now there's a plus here, e of t. Okay? So this is a wave that is moving in what direction, right or left?
Right.
Yeah, this is a right moving wave. How do we know it's a right moving wave?
It's of x minus something t minute.
Yeah. Essentially, the way you find out if it's right moving or left moving, you just say, okay, I'm going to follow a phase as time progresses. So that means that you want to follow a constant value of the argument as t increases. So as t increases, for this, for this argument to be constant, x must increase, right? So that means that x is, when x increases, you're going to the right. Similarly, for this guy, when t is increasing, for this to be constant, x must decrease. Otherwise, the whole thing will increase, right? So that means this guy is representing a left moving wave, okay? So let's call this, say, psi1, and let's call this solution psi2. So these are linearly independent solutions, right? Because, this function and this function, they're linearly dependent. Okay, so psi1 and psi2 are linearly independent one. Okay, let's call it one, observation one. Now, observation two is that, do they have the same energy or different energy?
Same energy.
Yeah, because we saw there, the energy is given by p squared. And when we square this, it gives me the both. So the sign of p is just telling me which direction the wave is traveling. So they have same energy, right? And so when we have, okay, let me make that the same comment.